Okay everybody, another riveting demonstration for you this morning. I've got a battery here, and that battery is connected to this length of wire, which is connected to this length of green wire, which goes up here, down through that cardboard, down through the cardboard, and back to the battery again. It's just a simple circuit of copper wire, right? It's insulated wire with a green insulation. Now, I've got some compasses here, some very cheap compasses. But what you'll notice is they're all pointing the same way. And they're all pointing north. Or pretty much as good as they will get at pointing north. They're all pointing in the same direction. And you would expect compasses to do that when you put them in the Earth's magnetic field. But here's something a bit strange. I'm going to move these little compasses and move them around the copper wire there that's got a current flowing through it. Right, I'll set them up and then we'll come back. I'm back. Now, first thing to notice is they are not all pointing now in the same direction. But more importantly than that, they are all pointing in a circle around the copper wire. There's a magnetic field produced around that vertical copper wire, and that magnetic field is circular. This was first discovered by a guy called Ørsted. Now, when you pass a current through a copper wire, then a magnetic field is produced around that copper wire. And the size of that magnetic field depends on the size of the current and how close you are to that copper wire. So it depends on the current, and it depends on the distance that you are from the conductor. Let's investigate that a wee bit further. I've taken all those compasses away. I've just left one in, and there's no current flowing. I've disconnected my battery. But watch what happens. Watch what happens when I connect the battery, and the current's going to flow in one direction. Okay? Now I'm going to reverse the current. So I'm unplugging the battery. I'm turning the battery around, plugging it in the other way. The magnetic field has changed direction. Let's do that again. Swap the battery. No battery. So by changing the direction of the current, we get the direction of the magnetic field. Now there's a way you can work that out. So I'm going to connect my battery so that the negative terminal is here and the positive terminal is here. So the current is going to be flowing in this direction, up through the bottom and up through the wire. So it's going to be current flowing vertically upwards, and we're going to see what happens to the compass needle. There's no current flowing just now, but I'm now going to plug this in. Watch what happens to the compass needle. That compass needle is pointing, the blue part of the compass needle is pointing upwards, towards north on that compass, if you like. In fact, the magnetic field is pointing in a clockwise direction. If I move that, always moving clockwise, that's when the current is flowing upwards through the cardboard. Now watch what happens when I reverse the current. I'm going to reverse the current on my battery pack, so the current's now going to be flowing downwards through the green wire. And the magnet has now flipped, the compass has now flipped, and it's now pointing anti-clockwise. Now no matter where I put that around that conductor, it's pointing in an anti-clockwise direction. So the direction of the current affects the direction of the magnetic field. And we switch it again. Let's switch the polarity. Did I move? Switch it again. Switch it again. So reversing the current reverses the magnetic field, and the magnetic field is circular around that conductor. And there's a way that we can remember the direction of the magnetic field in terms of the direction of current, and it's called the left-hand grip rule. Your thumb shows you the direction of the current. So if my thumb is pointing upwards, if the current was flowing upwards, then the direction of my fingers shows you that clockwise magnetic field around the conductor. Left-hand grip rule shows you the direction of the magnetic field around a current carrying conductor. Okay? Right, let's have a wee bit of a closer look at that then. A magnetic field is produced around a current carrying conductor. If there's a current flowing in a wire, there's a magnetic field produced around that wire. And that field is circular in cross-section, or cylindrical along the length of the conductor, if you like. And we can demonstrate that using the left-hand grip rule. So there's a wee diagram of what that field looks like, cylindrical in nature around the conductor. If we look down from above, that red dot in the centre there is the wire, and if we imagine that the current is coming out of the screen, then the magnetic field is in a clockwise direction around that conductor. And again, we can get an idea of what that looks like using the left-hand grip rule. So if that's our view from above, then there's my left-hand grip rule showing you, my thumb shows you the direction of the electrons or the current, and your fingers show you the direction of the magnetic field. Now the size of that magnetic field then decreases the further away you are from the wire, from that current carrying conductor. So the size of the magnetic field B varies with 1 over the distance. Now notice it's not the distance squared here, because this isn't a point source, it's not a spherical relationship, it's a circular cross section. So it's B varying with 1 over R. Now also, the larger the current is in the wire, if you have a larger current, you're going to get a stronger magnetic field around the conductor. So B varies with the current. The size of the magnetic field increases as the current in the conductor increases. So B varies directly with I, and we can put both these relationships together. So B varies with I over R, and if we introduce a constant, then we can say B equals a constant times I over R. Now the constant in this relationship that allows us to work out the magnetic field in Tesla is usually expressed in this form, that bracketed term there. And the way you would say it is mu naught over 2 pi. Mu is a Greek letter, and mu naught is on your data sheet. Mu naught has got a value of 4 pi times 10 to the minus 7 henries per metre. Now, we'll meet henries when we do inductors a little bit later on, but that constant mu naught is called the permeability of free space. Remember, we met the permittivity of free space when we did electric field equations. Well, this is the constant associated with the magnetic field equations, mu naught, the permeability of free space. And in the equation, it's mu naught over 2 pi. And the more astute amongst you may have noticed that if you do 4 pi times 10 to the minus 7 over 2 pi, you get a constant, you get a shortcut of 2 times 10 to the minus 7, and you can use that shortcut of 2 times 10 to the minus 7. Same as we use the shortcut of 9 times 10 to the 9 in electric field equations, then you can use 2 times 10 to the minus 7 in magnetic field equations. Now this relationship then allows us to work out what the size of the magnetic field will be at a certain distance from a current carrying conductor if we know what the current in that conductor is and we know how far away we are from it. It doesn't crop up that often in past paper questions, but let's have a look at a wee example. So this is from the 2016 paper. It's a student measuring the magnetic induction at a distance r from a long straight current carrying wire using the apparatus shown in figure 14. He's basically got a magnetic induction meter there. It's measuring the size of the magnetic field at a distance r from a wire that's carrying a certain current in it, and we have to calculate the current in the wire. So we're going to use the relationship from the previous slide. That relationship is of course on your relationship sheet. We'll rearrange it for current and substitute in for B and R. B was 5 times 10 to the minus 6. R was 0.1 metres, and we're using the shortcut of 2 times 10 to the minus 7 for mu naught over 2 pi. That gives us a current of 2.5 amps. 3-mark question. These meters, you could buy these meters in B&Q. A builder would use one in your house if he was trying to find wires behind your wall. Maybe putting a nail into the wall, you don't want to hammer it into a live wire behind the wall. House builders will also use these meters. There's building regulations about how close you can build houses to overhead pylons and overhead wires. So they would use these meters to detect the size of the magnetic field so that they're not building your house too close to the overhead wires. That's it then, the magnetic field around a current carrying conductor. We'll see you in the next one.